I'm Proto. I work at OP Labs. I'll wait for the last few people to get seated. So this is the fault proof workshop. Now, fault proofs are in development. So I'm just going to put a disclaimer here. Like, this is work in progress stuff. It's bleeding edge. Beware, there may be dragons. This is what we'll be covering during the workshop. So I know, like, a lot of you may have not brought laptops, or you may not have the right setup to get through a lot of the fault-proof stack. And we only have 20 minutes. So I'm going to provide you with all the context about the design and like how to run these things and how to build on top of it. And then I'll cover a little bit about the implementation of the stack. And then I'll point you to the demo. And then after the workshop completes, I can help like everyone who wants to hack through a small demo that you can run on your laptop. So what's the fault-proof stack? What are these fault proofs? Well, they're also called like rollup proofs or fault proofs. And you have to think about the context. We already have a rollup. There's somebody sequencing. Then there's somebody able to submit the data so that others can replicate what is being sequenced. So the verifier replicates and verifies that the layer 2 is fully derived from layer 1 correctly. And then the output proposer is like a special kind of verifier, which basically claims this is what I've derived from the layer 1. Now, after all this processing, I think this is the result, and then post that to layer 1. And then how do you secure this result? How do you trust the output proposer? Well, that's what the challenger is about and what fault proofs are about. They watch the layer 1 for incorrect claims, and then the challenger corrects the incorrect claim by challenging, by submitting a counter proposal. And there are many ways to do this. Now, in our case, it's an interactive fault proof over the state transition. I'll explain what is being proven first and then how it's being proven. So this is what a layer 2 looks like abstractly. So if this layer 1 full of blocks, then we have a layer 2 that takes data from the layer 1 and converts it into these attributes. These attributes can then be processed by the layer 2. And we know this as a consensus layer and an execution layer. This is a model that we have been designing for to be compatible with the architecture of layer 1. And then with the prior state and the new attributes, you can produce the next state and then repeat and repeat. And so you can keep extending the chain. Now, when we are proving something, we basically make an assumption that there's a prior state that everybody agrees on. Then there's some new data that needs to be processed. And then there's some output state that has been claimed that needs to be verified. So there's 3 different types of data, like agreed data, witness data, and disputed post-state. And now what we are going to do is create a program that takes the agreed pre-state, applies the witness data in such a way that it can run in a very constrained environment without requiring a full node, such that it can be proven on-chain. So why is this so important? Well, if you think about proving something, you may think of layer 1. Now, layer 1 has this thing called client diversity. Tame from Test and Prot covered this in his workshop as well, where with some diversity, you get resilience. You get this ability to call out if there's a bug. And so we want this whole stack to be modular, so that there can be competitive alternative implementations. And then with all these different implementations, we hatch. We get the benefit of not having a single point of failure. And so this is what client diversity is like on layer 1. On the execution layer, there's still ways to go. But thanks to people like Tame and Test and Prot, we get more clients, we get more alternatives, and we're building the same thing in the proving layer. And so this is what it could look like. Disclaimer, very experimental. Now, we have OP-Gaf and OP-Node. These are essentially the reference implementations currently of the OP stack, what most people run. We can have OP-Aragon, and then there's OP-Ref. OP-Nethermind is in development. So there are many options. And then what we want to do is take the part that runs the state transition, take the part that changes the state, and then prove that with different proofing modules. And so we have Canon. Canon is the one that's now currently in development by OP Labs. But then there are other options, potentially a RISC-V proof. And then when combining these versions, we get different outputs. And then we have to secure the output proposal on layer 1. We do not rely on a single implementation. So this is what really like layer 2 architecture is about. It's how to enable proof diversity by making a clean interface such that we do not depend on like this monolithic thing that secures the whole ecosystem, but rather we enable small teams in the ecosystem to compete and create the best implementations to secure the chain. And so what does this interface look like, right? This is the basic version. There's this idea of an external world and an on-chain world. Or really the external world is where you get all your data. On-chain is just like the constrained environment where you just want to replicate the computation. This thing, it's too expensive to run on-chain in one go. So what you do is you want to emulate it in a proof that can be verified more succinctly. And so now think of the interface as something that you can separate, and then you can put Canon in between. Canon is the fault-proof virtual machine, and Canon allows us to generate a trace of the execution while collecting the data from this external server in such a way that others can reproduce the trace. And when you have a trace of execution steps, then you can create an on-chain fault-proof with verifiable instructions. So that's the fault-proof virtual machine. Execution trace proofing. Now, how does this virtual machine run, right? Like it's quite a lot to reinvent a computer just to verify a small program. So what we really want to do is simplify, oversimplify maybe, such that we can just prove the things we need. We don't need to prove everything, but we do want to prove this very minimal instruction set called MIPS. And then with this bare metal kind of environment, where there's not a lot of environmental access, there's no file system, there's no sockets, no no internet. And so what you really have is a limited sandbox environment that can execute one instruction at a time. And then we can prove that instruction execution. And so it kind of looks like this, where you have a memory root, a program counter, some registers, an exit code, the state of the virtual machine. And changing the state here is a lot easier than changing or processing an EVM transaction. This right here is only a few hundred lines of code to just parse the instruction and apply it to memory, because you only have to change a little bit about the memory at a time. There are not these huge, complex instructions that exist in the EVM. And so, well, you repeat it a billion times. These instructions are very simple, but you have to do many of them. But this is not a problem, because we get to bisect the execution trace on-chain. We don't have to prove all of them. We only have to prove where we converge. So when there's a on-chain claim, and then there's a challenger trying to disprove the claim, then you bisect where the disagreement is, and then just use the instruction execution as a base case to resolve a small point of in a dispute. So this is what bisection looks like. It's basically like a binary search. You have a root node, and then from the root you go down, and basically the root commits to 100%, and then if you disagree with the root, you go to the left, you go take 50%. If you agree with what the person claims, but still disagree with the root, then you can counter by agreeing on the previous 50%, but bisecting to the right. So you make your way down to the bottom of the tree, and then you execute a single instruction. Now, okay, we talked about the virtual machine. Now, the OP program is what expresses, what implements the state transition that we have described. So the OP program, it implements this transition of going from pre-state, applying a block, producing the post-state, and then it is bootstrapped with the contextual information, the information that describes the game, which is basically a reference to the latest layer 1 data. That's where all the data has been posted. So there you can find all the inputs, and a reference to the previously agreed state. So this is an undisputed state that you can build on top of. Now, to really put it all together, there are specifications to enable anybody to write one of these modules, to write an OP program, to write a version like Canon, or to implement part of the specifications like the consensus layer or the execution layer, to make those modifications that you need to participate in this ecosystem to become part of the stack. And then these are the fault-proof specifications that I highlighted. They're open source, you can find them on GitHub. And then, well, if we take those specifications and dumb it down, this is kind of what it looks like. We have this idea of layer 1 history. We need to find our dispute, and then we create this dispute game. And then the dispute game basically turns into the same kind of EVM execution as you would do with a full node, but just for a subset, for a slice of the chain. You want to go from the previous state to the next state that has been disputed, so that you can compare, and then you can signal to the verifiers whether or not the claim was correct. And so there's this epilogue, basically, where you inspect the state after having processed the data, and then compare to the claim, and then exit the virtual machine with a 0 or 1, just like you're used to in a regular environment outside of the Onchain verification. Now, OP program, it's open source. It's based on GAF as well as the OP node. It pulls in the consensus layer part of the state transition and pulls in the execution layer part of the state transition. And then it does this very interesting thing called stateless processing. This is something that has been suggested for layer 1 as a native feature. But because of bandwidth, this is something that you can't really do. You can't just give all the pre-image data to a node just to process the block. But in the case of fault-proof, you have 7 days to process it. So it's really not that much of a problem to get a few more megabytes of data to process a block. And then by doing this, you get to statelessly verify what happened between state A and then state B. And then basically signal what the outcome is. Now, this doesn't require new state transition logic. You pull in existing code. So this ensures that we don't have to reinvent the EVM just to prove it. So there's no separate proving implementation of the EVM from the regular implementation. It's the same code. And so if you compare this to some of the ZK EVM work, this is one of the major differences in our approach, where we don't want to duplicate complexity. We want to have alternative implementations to create resilience, not to create mismatches between what has been verified on-chain and what's happening off-chain. And then GAF doesn't have to change at all. All through interfaces, we implement these abstractions that hide the database and then load the required data. Now, Canon is the fault-proof virtual machine. This is what enables this thing to be proven. Now, Canon is a MIPS virtual machine. MIPS is decreasing in popularity, so we are looking at adopting other proving systems. Now, Canon is also big endian. This is like the layer 1 EVM makes things quite convenient to prove. You don't have to do a lot of magic to try and like mangle those bits just to change the endianness. And then, well, Canon is both a Solidity implementation of MIPS as well as a Go implementation of MIPS, where the Solidity implementation and Go implementation, they both verify a single instruction in just like a few hundred lines of code. And then we use the Go implementation to produce the witness data efficiently and to go through billions of these instructions. Whereas the Solidity implementation, obviously, it's slower, it runs in the EVM, but it can verify one instruction statelessly. So this is kind of how you use Canon. Canon basically wraps around the server. So I highlighted there in the bottom. I hope people see it. There's a server flag where basically we take the OP program host, the thing that collects the data from the layer 1 and layer 2 nodes, that creates the preimages. Those preimages get served to Canon, and Canon passes them into the emulated program so that the program can process Ethereum statelessly and then come up with the result of the proof. Now, this is the RISC-V version of Canon, some side project I've been working on, where Asterisk enables us to prove more than just MIPS, like allows us to prove RISC-V. And so, as you might know, Rust doesn't compile to MIPS without going or jumping through a lot of hoops, but RISC-V does. RISC-V enables you to build a Rust program and verify the Rust program with a fault proof. And so later at the end of this workshop, I'm going to give you like the right directions to build your own programs that you can prove with Asterisk or Canon. And so Asterisk, it's an implementation from scratch. It's completely written in YUL. It's just like this, like assembly pseudo language mixed into Solidity. Now, Asterisk does not have floating point support. Well, Canon also doesn't really, but the Go compiler does have soft float support for MIPS. So this basically means maybe no machine learning in your programs, no floating point operations, but the EVM does not use any floating points, so this is not an issue. Now, okay, now this is the challenging part of the workshop, and I'll give you like an introduction on how to go about customizing your own fault proof. When you run OP program and Canon, this is like the most beefy version of the fault proof, where you want to prove an hour worth of layer 2 execution in a stateless manner in a slower emulated virtual machine. This is going to take some resources. However, you can do a smaller program, get the hang of it, and learn with a toy example. And then you can move on to customizing the OP program and Canon to prove your OP stack customizations. So we're going back to this image where the server is providing this data to Canon, and Canon is passing it on to the emulated client. And this is what we want to customize, right? Like if we don't want to have the exact EVM customization or EVM implementation as the OP stack, then we need to change the data that we're importing into the execution so that the execution can, process the new type of transaction or whatever you might introduce. And so we're going to replace the OP program server, and we're also going to replace the OP program client, but we're going to talk the same interface as the OP program does with Canon. And this interface is a combination of hints and preimage requests. Now, what a hint does is signal to the server that some preimage needs to be prepared. Now, the OP program, it understands exactly what it's trying to process, but Canon is just a MIPS virtual machine. Canon doesn't even know about Ethereum. So what the program does is when it tries to fetch a block, then it signals that, oh, I need the header, and I need all the receipts, and I need all the transactions. And now go prepare that for me, because I'm going to ask it for the data next. And then the server can go on its way, like stall the emulator, pause it, fetch the data, if it's not already there in the cache. And then once the data is there, then the requests from the client, from the OP program, they can be served immediately. They can, the program is none the wiser that there was an RPC request in the background. The execution of the virtual machine is fully deterministic, so that every verifier, regardless of what it takes to fetch the data, runs the same. And then, well, the program, just to emphasize, it runs in MIPS. The rest runs on your native computer, which might be x86 or maybe ARM, like a, like a MacBook. Now, okay, so this is what we're customizing, custom program, and then we're creating a special program server. Now, I don't want to create like a very extensive API just for a toy example, but I did create this demo, so you can run on your laptop through a very simple implementation of the client and of the server. The server is set up such that it creates the right file descriptors that communicate these pre-images and hints to the emulated program. It's an API. And then the client is implemented to fetch a few basic inputs, process them, and then verify them against the claim. Now, this might not be readable. I recommend for like the actual like hacker workshoppers to clone the repository right there, the link. But I'll try and describe what's happening here. So this is the client part of the program. So at the top, there's a bunch of setup where we create these channels that we communicate our pre-image data over. And then there are two types of keys. There's the local key, and then there's the hash type of key. The local key allows the program to ask for a bootstrap value for something that's known to have a certain value by the executor, but doesn't exactly match a previously known hash. So this allows the virtual machines to start in the same state, but then depending on the game, depending on this bootstrap value, to go and do a different task. And so depending on the block number, you might want to prove a different layer 2 block. Now, in this case, it's quite simple. It just asks for the pre-state, which is the number. It asks for a diff. This diff consists of two numbers, and then it takes the pre-images, the data that's behind these attributes, and then it can do just like a very simple state transition. The most simple thing I could think of is literally just a math formula, like, oh, just multiply the pre-state with a new number, maybe add something, and then the result you can just hash, and you can compare the hash to the claim. If that checks out, then you know the proof was valid. If it was not valid, then you want to exit in a different way. And so through the exit code of the virtual machine, you can signal what the virtual machine thought of the execution. And this is nice because this way you can create arbitrary validation conditions. It's not just about proving an output route or about proving a state. You can literally implement something like process all Uniswap swaps, inspect the trades, accumulate the volume, and like compare the volume to the claimed volume. You can do very like in-depth queries by expressing the program your way and then reusing the same Canon stack. And so what I hope to see from hackers during the Istanbul hackathon is to, like try and build a different program, something that's not a layer 2, but something that uses the same stack, and then permissionlessly prove computation. large computations that you might not otherwise prove in a ZK virtual machine. Okay, that's the workshop. If anybody has questions about the demo, I'll be glad to help. But I think that's all. Thank you. No questions? Right. I'll talk more about MIPS. So MIPS is one of those instruction sets that's been around forever and likely will be around for quite a long time from here still, because it's so widely spread. But companies like Google have stopped using it for Android, and overall the adoption has stagnated. And so while it's a very elegant, simple instruction set, it's very easy to prove, which, like less complexity means more security, more less risk in proving what you're trying to prove. It has lost the adoption, and so we want instruction sets that have good support from programming languages like Rust to increase the amount of programs that we can prove. And so RISC-V is like the newer version. It's also a reduced instruction set, similar to like MIPS. It's a few more instructions, but this allows you to prove a RISC program as well as a Go program. So I think this is the future we're working towards. WASM is another beast. So WASM does have a few more instructions that are a little bit more complicated than these RISC-V or MIPS instruction sets. But it could be a good option. I think several different teams are already working on WASM proofs. I know Arbitrum, for a fact, has a custom version of WASM, like a modified version that runs their proving system. But then I also think different teams outside of Optimism and Arbitrum are working on WASM proofs. Question over there. So basically, what I think of the sorry, I'll repeat the question. So if there are very custom applications, like different programs that people want to prove, I think we should support that, just because all those contributors can help improve the virtual machine. But I do not think we should add complexity to the virtual machine just to increase the amount of use cases here. I do want to focus on the layer 2 use case. However, like I showed you, the interface right there it's just 3 binary communication channels. There's not a lot of API surface, and so I think people can be very, very creative with what they prove. And so I hope to see more than just layer 2. Tim? So yes, good question. So whether or not we can migrate from MIPS to RISC-V. Well, with the multi-client infrastructure, we can use both at the same time for a while. And then, like once we're confident in the new proving system, we can phase out the older one. And the nice thing about Go is that it supports both MIPS and RISC-V. So the same program, the same definition of the OP program, you can just define it. You can run a different command with the standard Go compiler. No customizations needed to target a different architecture. Okay, thank you, everyone.